Okay, so wherever you're at, please pause and have your colored pen up. And I want lots of answers today, so listen for your number. And here we go. Tell me your answer to this question. I got student number 17, 24, 18. Student number 17, what'd you put? Okay, student number 24.
Oh, sorry. I got 182.
You said 176? 182. Student number 18, what'd you put?
I said 176.
176. Student number 11, what'd you put?
182.
182. So we kind of split 50-50. Student number 4, what'd you put? Student number 4 is absent. Student number 10, what'd you put? Student number 2, what'd you put?
182.
Student number 14, what'd you put? Student number 8, what'd you put? 182. Student number 6, what'd you put? So we seem to be pretty divided between 176 and 182. We're divided by 176 and 182. Catalina, yes?
I say I agree with 182, but not just 182, but 182.
Okay. Davis?
Oh, I've got it.
I agree with 176
Okay.
because
Well, don't tell me why, but you agree. I appreciate you telling me 176. Zabari and then Chris? 182. We're kind of going back and forth. Chris?
Well, if we're going to be technical, then I agree with 182 feet squared.
182
okay,
feet
well,
squared.
sorry.
No.
Okay. So, well, I will say that one of the answers is correct and one of them is incorrect. But as I've been trying to emphasize to you for a long time now, it's not so much the answer, it's the process. But in this case, I'm not going to reveal the answer, but we will start gathering.
What? Oh my gosh.
There is no answer. The answer is.
So let's gather what we know first. Could someone tell us first thing that you figured out? What was the first thing that you figured out? Michaela?
Okay, the bottom side, where it says 48 feet.
Yep.
You can divide 48 by 3 and you get one side, so 16.
Okay, so now why are you allowed to do that? What evidence was there that you could divide that 48 by 3? Go ahead.
They're all congruent.
Okay, so they're all congruent. And that one piece of information told you that that was going to be 16. So absolutely. Okay? Brandon, what else did you figure out? Don't tell me an answer. Tell me what else you figured out.
I found out like the top of it.
The top of the whole structure?
Yeah. Because when I
Mm-hmm.
set it and then I figured it was a parallelogram.
Okay.
And then I remember we saw in yesterday that the opposite sides of the parallelogram are congruent with each other.
Okay.
It's not just 16 and then like
Okay, so you knew that the top was how much? Okay, so this distance from here to here is going to be 32. Okay, I'll buy that based on what we figured out so far. And we already know that the bottom is 48. So we now know part of the structure is going to be 48 plus 32, that's 80. So we know we need at least 80 feet of material. But what about these little diagonals in between? What did you figure out about those, Davis?
Well, I first figured out that they had to be bigger than 15 feet
Mm-hmm.
because when you have something at an angle, and whatever size it is, it's that size, it's actually shorter than when standing straight up.
Okay.
And I took a wild guess on this, but I just thought since the bottom part there, each one of those were 16, the top part there, we divide those by 2, they're also 16.
Okay.
I just guessed that they were all pretty much similar as well.
Okay. So you're saying that this diagonal is also 16?
Yeah.
Okay. And so if we do that, we end up with what type of triangle? If I draw this in and we say that that's 16 and that's 16, what type of triangle does that end up being? Brian? Equilateral. So it's an equilateral triangle. We got 16, 16, 16, and it doesn't even really matter because now you can just say how many of these segments do we have? They're all 16, and count them up and multiply by 16. And so Davis, you ended up with what answer?
176.
176. Okay, and there was quite a bit of agreement to that. Zabari, you had something else.
I didn't do the whole guess 16. So because I said my theory was because all R's are supposed to be equal. I said that each triangle was an isosceles triangle.
Okay.
So what I did was I did a perpendicular bisector for one of the triangles.
Okay.
And that way it made it cut the triangle in half, making it a right triangle.
Okay.
So side A would have been 8 feet, and then since we know that the height of it is 15 feet,
Mm-hmm.
so we know that the perpendicular bisector is going to be 15 feet, and using.
So you're saying this is 8 because it's a perpendicular bisector,
Yeah,
and then we knew that this was 15. How did we know that?
because this is the height of the whole thing.
Oh yeah, it says it right here. It's 15. So this is 15, and that's 8. Okay.
And using a Pythagorean triple, we know that it's
8, 15, 17. That's a Pythagorean triple?
Yep.
Oh yeah, it is. So then by that, you're saying that this would have to be 17. But he said it's 16 because it's equilateral. But you're saying it's not.
It's isosceles.
You're saying it's isosceles.
Yeah, it's not.
So, I'm not sure which one it is, but we got 2 different results, and one of them is correct. So, we've got lots of evidence here. I don't know if this is correct or not. I'm not going to tell you the answer. We're going to come back to this at the end of today to see how you have.
Who?
Really?
So we see how your brain processes this to see if you can actually modify what you say. Because, I mean, we were literally split almost 50-50, which means that half of us have to change the way we thought about it, and half of us need to keep it the same. So let's see who, over the course of today, modifies what they thought. So we're going to actually come back to this page towards the end, okay? So don't mark your answer correct or incorrect. Just leave it the way it is. And we're going to get on with today's lesson. I'll answer 2 more quick questions. Jada and then Davis.
Could you give us a hint as to what the
Number.
Davis.
Now that I've seen how Zabari did it, I just started out the way I did it.
You're starting to doubt what you did. Okay, we'll see how we do. So, of course, today's lesson is 7.3, and we're going to be using similar right triangles. We have a lot packed in. However, we've got a head start because we did an investigation yesterday that helped us along a little bit. So, we learned a little bit about geometric mean, which is going to come into play a little bit later. So let's start with our objectives. We are trying to walk out of this room today with a foundation of how to use geometric mean to find missing links in a right triangle, and how to apply similarity with the right triangles. And so the new vocabulary of the day is not really new because you were introduced to it yesterday, and it's a geometric mean. So, let's start with the cheat sheet. As I said, I gave you a new one because I somehow omitted two major ideas. It was a total accident, and I apologize for that. Now, this theorem doesn't have a fancy good name. So unfortunately, we're going to stick with theorem 7.5. But as you know, it doesn't really matter the name. The most important thing is knowing the idea. And the idea is that if you take a right triangle, draw the altitude from the right angle to the hypotenuse, you then divide the triangle into two more triangles for a total of 3. And those 3 magically will be similar to each other. And so we start with this original triangle, draw the altitude, and then we get this triangle and this one. And notice the letters. We use these letters here. The same letters are here, marking the different vertices. These 3 triangles will be similar, and that's stated in these similarity statements right here. The first minor objective of the day is to know how to write out the similarity statement, making sure that our letters are in the correct order. You learned a long time ago that the order of the letters matters. So that's going to be our first small objective of the day. We'll get to that in a couple of minutes. Any questions so far? You probably do, but we haven't even experienced anything. So now, the second thing on your cheat sheet is the geometric mean definition. This is not a theorem. This is just a reminder of what geometric mean is. We already explored it yesterday. So you can say it 2 ways. X is going to be the square root of a times b, or you could say x squared is equal to a times b. That's a geometric mean. Now, we have the 2 theorems that I accidentally omitted from your cheat sheet and then had to replace your cheat sheet. There's the geometric mean theorem, and there's 2 versions that are basically the same idea, a different viewpoint. So one of them is called the geometric mean altitude theorem, and one of them is called the geometric mean leg theorem. I personally cannot stand the complexity of the way it's written out in words. I think it's an injustice to understanding what's going on. So what I'm going to do is I'm not going to bother going over the terminology right now. But what I'm going to say is that there's a connection between these lengths and their values and the geometric mean. Okay? So I'm going to kind of reserve this one for a little while. We're going to build to it. And the same thing with the leg version, which is worded even more horribly. I mean, I personally, the length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. Excuse me?
What?
Exactly. What? I don't know what that means, but when we go over it in a little while, it will become, in my opinion, perfectly clear. And so, again, I'm going to reserve this. Okay? I'm going to reserve this. In fact, what I would like you to do later on, after we go through some examples and checkpoints, is you're going to go back to your cheat sheet, and you're going to write in a couple of little notes that's going to make this very clear. Because the point of the cheat sheet is to help you, not make your life more miserable by trying to understand some bizarre, strangely worded theorem. Okay? We want our cheat sheet to be practical. Any questions? Good. So let's jump in. So let's talk about what's going on. And here's where I think you just need to watch for a couple of minutes. You're going to be doing a lot of sketches today. You're not going to be using the ruler. But you're going to be doing a lot of sketches. But for the moment, I want you to watch. Okay? So here we have the same picture that's on the cheat sheet for theorem 7.5. So, and then you see underneath it that it's split into 2 other triangles. So I want to show you what's going on here. That we've got this triangle. Once you form this altitude, this triangle comes out. And then this triangle comes out. Okay? But I did something a little bit different here. I don't have the vertices labeled. I have each segment labeled. Okay? So let me go back. All right? So I want you to look at this side, and this side. Notice that I use the letters A, B, C. Just like when we studied the Pythagorean theorem, A, B, C. A represents which leg of the right triangle? Catalina? The smallest leg, okay? So that's why there's an A here and not anywhere else. Because we're looking at this big triangle on the outside. But then we draw this altitude, and now we've got this, okay? So I want you to look. Here's the A. It's the small leg. And so that's the same segment right there. Watch. I'm going to put it back, and I'm going to move it forward. You see where it came from? So what is the length of this side right here? Jabari? That's A. But now tell me, which side of the triangle is that? Brandon? That's the hypotenuse of the small triangle. So the short leg of the big triangle becomes the hypotenuse of the small triangle. What about this side? What would we label that side? Thumb?
H.
That's going to be H. So in this big triangle, that's actually not one of the sides, that's the height. And that height all of a sudden becomes the large leg of this right triangle. We don't know this distance because the C is actually the whole distance. We don't know this distance, so we're going to put a Y right there. So what is going on, and this is where it's going to take you're going to give yourself a little time to digest and understand, is that we split the triangle into another triangle, and parts of the original triangle become new parts in this new triangle. This length is equal to this one. Now, I've got this one. So I want you to look where it came from. And now, help me label the sides. What is this side going to be called? Sebastian? That's H. And I want you to look. Look at this triangle here. Which side of the triangle did we just label H? Alicia? The smallest leg. And the H was which leg of this triangle? Yeah, it's the larger leg. And here it's the smaller leg. What is this going to be? Maria? That's going to be B. What was B in the original triangle? Davis?
The lowest, the hypotenuse.
Well, you got a 1 in 3 shot. This is the hypotenuse.
It's the lowest leg,
It's the longest leg, but what did it turn into in this triangle?
the hypotenuse.
The hypotenuse. Okay? And we don't know this side, so we call that X. And so what happens is that if we're missing a piece of information in this picture, there's a relationship going on here. So now I'm going to rewind this whole thing and show you one last part that's the critical piece. So now let me move this triangle and I want you to watch. Try and do it perfectly. Not quite perfect. And now I'm going to take this one. Now what do you notice? Well, watch this. What do you notice about the triangles? Brandon?
I mean,
They are similar. And so, in fact, and unfortunately, because of the way I constructed this triangle, it's actually difficult to, let me see if I was able to do that. Now, put that back. It's not going to let me do it. Yeah, I did do it. Okay, so if I take this, the big one, And if I rotate it a little this way, so watch. They are all similar to each other. One second. So that's what is going on in theorem 7.5. That's where we get these similarity statements. Here it was harder to see because they weren't rotated around. But what happens is that we get three similar triangles. And because they're similar, we can actually find pieces of information because they're now proportional, which is what we spent a large part of the last chapter studying, that similar figures are in proportion. So we're going to utilize this idea to solve some problems. Okay? Any questions? Brandon, you had been waiting?
I was going to say there was a question.
Okay. All right, so we'll see how we did. All right. Any other comments, questions, any observations? Okay, so now let's actually put it into practice. First goal, as I had indicated before, was to be able to figure out which triangles are which. So we're going to just start out by identifying the similar triangles from this picture. We're going to stay organized. We're going to keep it very simple. So start with the big triangle. Start at the right angle so we stay nice and organized, always looking for the right angle. So the big triangle starts with the T. That's the right angle. And now either go along the longer leg or the shorter leg. It doesn't really matter, but pay attention to which way you go. So I'm going to go T, R, S for whatever reason. So I'm going from the right angle along the larger leg, along the hypotenuse. So now, what's the second triangle? So here's where a sketch is going to come into play. So notice how this triangle is. We drew the altitude. And so now I want to figure out this triangle right here. So what I'm going to do is I'm going to redraw it, and it's a sketch. So I'm intentionally not going to use straight lines. I'm just going to sketch a right triangle. It doesn't matter, not that bad, but try to make it somewhat reasonable. And now I'm going to label where everything goes. And that's going to help me. So this point right here, what started the right angle? The right angle is right there, so that's the U. And then if I travel from the U along the longer leg, I end up at the R, so that would be the R over there. And then the T would be right here. And so now it's very simple for me to figure out the next similar triangle if I just follow the same pattern that I did here. I went T, R, S, so now I'm going to go U, R, T. And so we'll write out triangle U, R, T. The third triangle is right here. So I'm going to sketch that. Just going to sketch it out. So it's a bit smaller. Again, doesn't really need to be very perfect. And now again, I'm going to pick out the right angle is the U right there. And that's going to help guide me. The smaller leg goes from U to S. This is my smaller leg, so the S must be up there, and then the T must be over here. And now follow the same pattern I just did. U, T, S. And so now I've got triangle U, T, S. So we're able to identify the similar triangles. This is just laying the foundation for what we're going to be doing next. Does anyone have any questions? Because eventually, you've got to be able to do some of this mentally. You're going to start out today drawing pictures, but we're going to eventually be able to do it mentally. Any questions? Okay, see if you can name them on your own. And I want you to name them by starting at the right angle so that we can compare what we did, with our teammates. So start with the right angle. Each time you name a triangle. So you got 2 minutes. If you're already done, compare your statement with your teammates. All right. Well, just because it's a mouthful, I'm just going to go ahead and reveal the way I wrote it. Don't mark yours right or wrong. Take a moment, because you might have had your letters in a slightly different order, and we'll make sure that we understand. So, similarity statement has a triangle similar to another triangle, similar to a third one. I started at the right angle, went along to the longer leg, and then over to the other vertex. So I had triangle WUV is similar to triangle ZUW, is similar to triangle ZWV. If you have your letters in a different order, that's fine, as long as every letter matches. In other words, the W, the Z, and the Z have to be in the same place. So if your W is in the middle, then your Z has to be in the middle, and your Z has to be in the middle. So you can figure out yourself whether or not you got it correct. Any questions, keeping in mind that we have just laid the foundation for what we're going to do. We haven't even really done anything yet. Any questions?
When you write the similarity statement, would you put it from this biggest triangle to the smallest?
I did. I don't think it matters. Did you have it in a different order, like you had this in the middle over here or something like that? That's fine. That's totally fine. Thank you. That was a good question. The first person asked that. That's actually pretty important. Okay? So I don't think it matters, though. Any concerns? Good. So now let's build from there. And so now here is the big piece. Okay? Here is what Theorem 7.5 really says, or if we take it to the next level. I don't want you to write anything down. I want you to look first. What I've done here is I now have all three triangles that come from this all rotated the same way. Okay? So try and follow along this logic because this is the big piece. In this triangle, I want you focused on this. Excuse me. Just this. This is what you're focused on here. Okay? The middle triangle, of course, we're just looking here, here, and here. And in the smaller triangle, we're focused here, here, and here. Okay? We talked about the fact that they're all similar to each other. Okay? And so what that means is, if they're all similar, then this side to this side is in proportion to that to that. That's what you learned in the previous chapter, is that when you have similar figures, their sides are in proportion. So you see right here, forget about the rest and just focus on that I've highlighted. Long leg to short leg is going to be equal to long leg to short leg. Here's the long leg of the first triangle to the short leg of the first triangle. That's right there. Here's the long leg of the middle triangle to the short leg of the middle triangle. Right there. And so what this means is, if we have information missing, let's say that I have this, this, and this. We can now find that. When you have a proportion, if you have 3 pieces of information, you can find the 4th. Okay? So that's what is established here. And in fact, there's so many different relationships here that we can find any piece of information that's missing as long as we have the other 3 pieces. And so what you see illustrated here is all these different ways of creating relationships. In fact, there's even more, because we could take all of these and flip them upside down. We could trade the left and the right. There's a whole bunch of different ways that this can be constructed. But the point is that the triangles are similar, and we can find a missing piece. Okay? Any questions about that?
Wait, yesterday when we were doing exploration, does H2 and V come by here?
It will in a little while. So just hold off that thought. It's going to be important in a little while. Just for right now, try to focus on, and I put a few too many highlights up here, so let me back up a second. If we have 3 pieces of information, we can find the 4th piece of information. Okay? So we're going to use that idea. Any questions? All right, so now, in example 2, we have something similar to what we've seen already, except now I've given a similar picture and I filled in some of the pieces of information. We're first asked to identify the similar triangles, then find the value of x. I want to identify them a little bit differently. Okay, so follow along with me. I just want to show this technique, and then later on you'll decide what you want to do to make this work. I want to sketch the 3 triangles. So instead of writing out GEF, and then HGE, and then HFG, or whatever the order would be, instead of writing it out as a similarity statement, I want to actually sketch the 3 triangles, okay? So let me move this up. And I'm going to draw my sketches down here side by side. So here's the first triangle. I'm going to draw the original triangle. And again, it's a sketch, so don't judge me on my lack of accuracy or lack of perfection. But now here's the important part, labeling. So now this is E, G, F. Okay? All I did was copy. That's not a big deal. Now, I want the middle size triangle. The middle size is going to be this one right here. I already know it's going to look just like this except a little bit smaller, so I don't care what the letters are. I'm just going to draw a similar triangle and try to get it just a little bit smaller. But now I'm going to pay attention to where the letters go. I'm going to start with the right angle. H is going to be down here. I can see just by following along that the shorter leg goes up to G, so G's right there, and then F is over here. And now the smaller triangle is quite a bit smaller, so I'm just going to try and sketch a small similar triangle. And it doesn't really matter how accurate I am, as long as it's, approximate. But again, the letters have to be in the right place. So H is the right angle. Going along the longer leg, looks like this is G, and this is going to be E. So now I've drawn out the similar triangles. I could go ahead and make a similarity statement. It's not a big deal. If I wanted to, I could say triangle GEF is similar to triangle HGF is similar to triangle HEG. So I've identified the similar triangles. That's not a big deal. Okay? So we have a similarity statement, but that's not the most important part. The idea now is to use this setup to find this missing piece of information. So now watch the critical piece. Now fill in the numbers. Go back to the original picture. This is 3, this is 4, and this is 5 based on the original picture. Our goal is to find x. X is the distance from H to G. So here's x, and here's x. But now let's look at this middle triangle. Is there another piece of information that I can fill in? What else could I fill in? Fun?
GF is 4.
GF, if I just read it, GF is 4. Anything else I can fill in? Brian?
EG is 3.
EG is 3, not in this picture, but EG is 3 over here. And because this is true, they're all similar, now we can set up a proportion with 4 pieces of information. So all I have to do is choose which one makes sense to me. I mean, if I just look here and ignore the rest, look at what we have set up. 2 similar triangles. Here is the small leg, hypotenuse, hypotenuse. Because they're similar, that's going to form a proportion. And so we can very simply figure out what the value of x is by forming the proportion. You could do 5 to 3 is going to equal 4 to x. Excuse me, that's not an x. Or you could do 5 to 4 is equal to 3 to x. Or you could do x to 3 is equal to 4 to 5. You can set up the proportion a whole bunch of different ways, but no matter what, it's going to come out to the same value. So go ahead and solve the proportion. It should take you 5 seconds or so. So what's the value of x? Dalton?
2.4.
You agree with that, Chris? It's 2.4. Or 2 2/5. Either way, it doesn't matter. So we've got the missing value, 2.4. That would have worked even if we had used this triangle and ignored the middle triangle. If I had done this, if we didn't even have this, and we just looked at the triangle on the left and the triangle on the right, well, I've got 3x, and I've got 5 and 4. If I did 3 to x is equal to 5 to 4, we'll get the same result. So no matter what way you go, you should end up with the same value. Does anyone have any questions on how we approach this? Any thoughts? Any observations? Okay, let's see how you do on your own. Checkpoint number 2. You got 3 minutes on the clock. A little bit more of a process. If there's time left over, compare your answers with your teammates. You can write them out or draw. Okay, so let's see how we did. You had a chance to work it through. You had a chance to compare your answers. Let's hear from a few people. I got student number 18, 4, not here, 18, 24, 16, and 6. Student number 18, what did you put?
Approximately 4.6.
Okay, student number 24.
Approximately
Student number 16. Student number 6. So we all seem to agree that it is approximately 4.6. A more accurate representation would be 60 over 13. That's exact. 4.6, as everyone said, was approximate. I'll accept either one. I didn't put the similarity statement, but you should have identified the similar triangles either with a drawing or with a statement of some sort. Does anyone have any questions on how we did this?
If we did it like on the test, would we put 60 over 13?
I'm a reasonable person. I'll accept either way as long as you're thinking about what you're doing. Okay? But one answer is exact and one is approximate. So think about that. Are there cases where an approximate answer is good enough, and are there cases where an exact answer is needed? Okay? Good. So today has been building, and we've been building to this. Got exactly what we had before. This is not different, but now you're going to do something. I want you to look, and do you see the ratios in red? Everyone find the ratios in red. Okay? There is something going on with all of them. So I'd like you to take a minute to just observe and see what you notice about the proportions that are written in red. Give me a thumbs up when you notice something definitive that you can say out loud and using terminology. Go 1, 2, 3, 4, 5, 6, 7, 8. Okay, you can put your thumbs down. So I'm going to help some of my other students along. I'm going to get rid of what's written in black. I know this equal sign is not in red, but just pretend that it's in red. And let's see if you notice it now. Give me a thumbs up if you noticed it now, or if you noticed it before. Either way. Okay, about half my students. Okay, put your thumbs down. Okay, let's look at it a little bit differently, because I'm not going to ask you what you observed. So now, I'm going to ask you to solve one of them. I would like everybody in this column of desks to solve this proportion right here. And I would like everybody in this column of desks to solve this one over here. And I'm going to be in charge of the middle one. Solve it. If you don't know what I mean, I'm going to be doing the one in the middle in a moment. But you should be able to do it on your own. So go ahead, solve the one that I assigned you. Write it out. If you already finished it, then go ahead and do the other one. All right? All right, so let's do the first one. Some of my students here in this column, what did you get? Start with Davis and then Ann. What did you get?
For the first, I got h equals the square root of y.
Okay, Ann, what did you put?
H equals the square root of y times x.
Okay, so we get h equals radical xy, or yx, doesn't really matter. And what about this last one over here? What'd you get? Jada and then Jeanette. Jada, what'd you put?
B equals radical or the square root of cy.
Okay, Janae, what'd you put? So we get b equals radical cy. Now do you see it? So what was the connection that you made earlier? There was a bunch of you had your thumbs up. Tristan, what was the connection that you made between all three? Okay. Okay. Alicia, what was your observation?
I was gonna say that in each of the equations, that one of the letters showed up twice.
Okay, so similar observation. So that's what I was hoping you would key in on. And Catalina had said something yesterday that was really important. Catalina, you had pointed out that the other two numbers, what usually happened if we set up a traditional style ratio, those two numbers end up being what? The extremes. And so the yellow highlight is called the means. Means and extremes. And so the mean is the geometric mean. In other words, this works out so that h is the geometric mean of x and y. So now watch what we just figured out. We just figured out, look at your cheat sheet, the new one I gave you, the two theorems can be summed up like this. The geometric mean theorem for the altitude is this right here. This is pretty much the entire theorem summed up. The reason the second version was more complex is because it actually represented two cases. And here are the two cases that it represented. Right here and right here. This is the geometric leg theorem, and this is the geometric altitude theorem, geometric mean altitude theorem. So what's going on here? Well, look at what has happened. We took this picture, look at the complexity, and then we took out this triangle and took out this triangle. And then we formed all of this and got these results, but now watch what we can do. Now we don't need this anymore. We don't need this anymore. We don't need this anymore. And we don't need this anymore. Because now we know this to be fact. So now we can go directly to this triangle. And based on the pieces of information we have, we can find a missing piece of information. So if I have x and I have y, I can find h. If I have h and I have y, we can find x. If I have h and I have x, we can find y. Same thing is true here. If I know c and x, I can find a. But if I know a and c, I can find x. So we can utilize these three equations that are basically summarizing two different theorems to find missing pieces of information from similar right triangles. So all the work that I just hid, all of this is the work and the evidence to support this here and makes the theorems true. But that's the whole point of developing theorems, is now we get to eliminate all that work and skip over it. Okay? So now let's go ahead and put it into practice. So now find x, y, and z. I also set up this first question so that we could go in a nice simple order. So I did make it a little bit easier to start with. So we need to find x, y, and z. We're going to start out finding x. And so what I'm going to do is get rid of y and get rid of z just for a moment. You don't need to erase it, but just so we can focus for a moment. And from the theorem, from the geometric mean theorem, we get that this distance, that segment, is going to be the geometric mean of that distance and that distance. So there's a relationship there that we can use. So 6 is going to equal radical 9 times x. Give me a thumbs up if you can figure that out mentally. Yeah, you should be able to. Good. Kasara, what's x? I'm sorry? Okay. I put you on the spot and you lost your confidence? Okay, I apologize. And x equals, yeah, x has to equal 4 because this has to be a 36, take the square root of it and it equals 6. Or, to get rid of the radical, you could square both sides and you get 36 equals 9x and you get x is 4. So no matter what, x equals 4. Brandon, you had a comment or question? Go ahead.
I was gonna say, I think the way where it was 6 squared.
And that's right. And so if you look at my work here, see this right here? That's another way to represent geometric mean. And if you look at your cheat sheet, it's written both ways, right? You can use it either way. You could say that a squared equals cx, or you could say a equals radical cx. Either way, it's the same thing. It's just a matter of deciding which one makes sense at the current moment. So now we know that x is 4. So this is really a 4. Now we need to find y. And so now you have to understand the other theorem. That there is a relationship between this distance, this whole distance, and this distance right here. But I want you to notice that. It's somewhat hard to remember, but if you pay attention, the relationship is this distance to the one that's adjacent to it. That's why that word adjacent is thrown in there. And it kind of throws you off a little bit. And we need the whole distance. That's why we had to find x first. But now we have all the information we need to find y. Because y will be the geometric mean of the whole hypotenuse and this little segment. So y is going to equal radical 13 times 4. No calculator needed. Just put it in simplest radical form. What will y equal? Got 3 people who figured it out? 4 people? 5, 6? Tristan? Very good. Y equals 2 radical 13. And so now we know y is 2 radical 13. Now we need to find z. And we have all the information we need already. The relationship for z is this distance is going to be the geometric mean of the hypotenuse, the whole hypotenuse, and this adjacent leg, this adjacent segment right here. So it's very similar to what we just did for y. But we've got z is going to be radical 13 times that segment, 9. Put it in simplest radical form. What do you get? Sebastian, what do you get? You get z equals 3 radical 13. And so we have successfully found all 3 lengths. And we used both theorems. Both the 2 different versions of the same theorem. Geometric mean altitude theorem, geometric mean leg theorem. Anyone have any questions or concerns about what we did here? Okay, so let's see how you do on your own. I'm going to put 4 minutes on the clock. If you finish and there's time left, then go ahead and compare your answers with your teammates. The relationship is height is going to be equal to square root of u inverse. All right, you've had a chance to work through it. You've had a chance to compare your answers. So now let's gather some answers. So I just want the value of u, just u. And I got students 16 and 18. Student number 16, what'd you put? Just for you. What's that? 27 and student number 18.
27.
So you guys agree that the letter U is 27. What about the letter V? I got student 11 and student number 1. Student number 11, what'd you put? Okay, student number 1, what'd you put?
For V, I got 9 radical 10.
So V is 3 radical 10. And what about W? I got student 12 and student 8. Student number 12, what'd you put? And student number 8, what'd you put? Okay, student number 17, what'd you put? Okay, student number 4 is not here, it's student number 21. 9 radical 10. So, after all of that development and all of that work, it comes down to knowing the relationships that come about from similar right triangles. That this distance is going to be the geometric mean of these two segments. Remember, geometric mean means you're multiplying this times this. And you need this distance to figure out V and W. And so this distance here is going to be the sum of these two times this one. The square root of that, the geometric mean of it. And then for this side, here, this distance is going to be the geometric mean of this whole distance and this. And so it's a matter of knowing and remembering the relationships. I think today, a lot of today's focus was about developing what was going on. But now it's a matter of knowing them, okay? Does anyone have any questions?
I see what you're doing, but it doesn't make any sense.
Okay? That's understandable. This is some of the toughest stuff we've done in a while. No doubt about it. So what I would ask you to do is give it some time and give it your best shot. If it's still not sinking in, still not making sense, my care class is open to you guys always. During testing tomorrow, it's shortened care and I'll be in here. Starting on Friday, regular care and I'll be downstairs. We're not quite done, but I'll answer 2 more questions, Brandon and then Catalina. Okay. Catalina?
I have no idea if we're asking the question because I didn't already say, but are all the questions going to be like this?
All of them, no. As always, you're going to see some things that we've done and some things that are asking slightly different things or radically different things. And it's a matter of you extrapolating what you've learned and applying it in different ways. It's supposed to be challenging. So you accept the challenge and you persevere through it to the best of your ability. Okay? So let me get to one real-world application. I am very low on time, so I'm really going to just focus on not really doing the question, but just looking at some examples. So one way to utilize these ideas is as an indirect measurement tool. And actually, this is, in some respects, pretty cool that you can do this. But if you want to measure something that would otherwise be impossible to measure, there's no measuring tape that's as long as a Douglas fir. There's no way you could get up on a crane and have someone hold a measuring tape at the bottom and you go up to the top and measure it. It's not practical. But it's a pretty wild method that you can use. You know your own height. And you could modify it or adjust it so that it was your eye level. Because that's what we're talking about, is where you see things. And you could very easily measure your distance as far as how far you were standing away from something. So you could measure this distance, and in this case it's 7.8 meters, and the height up to your eye level is 1.6 meters. You could actually figure out the height of this tree just with those two pieces of information. Because this distance here, as I've said a few times, this distance has a relationship between this distance and this one. And if you're looking for the height of the whole tree, if you're looking for this, well, that's the sum of 1.6 and this missing piece of information. So once you find this missing piece of information using the relationship that we've established, add it to 1.6, and it's no big deal. So what's the relationship again? The altitude is going to be the geometric mean of this and this. And so we have 7.8 is going to be radical 1.6 x. Solve that, and you've got the missing piece. Add that to 1.6, and you've got the height. Now, a lot of work that people do to measure things like this because of something they're studying or doing is done by using computers. So you can just take the measurements, plug it in, and it's done. But someone had to program the computer so it worked. So for example, a surveyor uses tools like this, which totally eluding me what it's called because I just learned it at the beginning of this year and now I can't remember. But this tool, you've probably seen contractors out working and they have this, something that looks like a telescope, but it's not. And they're doing some sort of measurements. So what they're doing, they're actually calculating angles. But utilizing these tools and some measuring tools, you can figure out how high something is that would otherwise be impossible to measure just by knowing your eye level and how far away you were from the object. By creating this simple picture and utilizing the relationship that this is going to be the geometric mean of this to this. Okay? So we were going to spend more time. In the interest of time, I just kind of showed it to you. And again, you're going to have to do some work on your own to try and figure it out. Okay?
The answer is 148.04545.
This one? 148 point what? Approximately 148 feet. Nice. Yes.
What's the answer for the warm-up?
For the warm-up?
Yeah.
So your homework is page 447, numbers 3 through 18, 21 through 26. 30, 31, and 32 is where some more effort's going to be needed. 32 is a proof with all of the elements filled in except 8 are missing. So I'm counting it as 8 points. You mark each one of those statements separately. That's a gift. That's to give you extra points so that you can get a better grade. And you're going to have a quiz on Monday. And that will be 7.1 to 7.4.